this presentation, I'd like to talk about calculating the mean and the standard deviation of a binomial probability distribution. Now, hopefully you saw in an earlier video where we calculated the mean and standard deviation of just probability distributions in general. I presented the two formulas, and we proceeded to do a couple examples. We can, of course, then, since the binomial distribution is a probability distribution, we can still use those same formulas and come up with the exact right answer, but because the binomial distribution is a specific kind of distribution, then we have a very specific alternate formula we can use that is much, much simpler to use than the other two for what we introduced earlier for mean and standard deviation. So let me introduce those formulas now. If I have a binomial distribution, I can calculate the mean, which is represented by the Greek letter mu. Mu can be found by the following. And remember, the two most important numbers in a binomial distribution are the number of trials, which is represented by n, and second thing is the probability of having a success for any trial, and that's represented by p. N and p are the two most important numbers, and hopefully you remember using n and p to actually plug them into the binomial formula in just the previous video where we used the binomial formula to fill out the probability table. Hopefully you did that. So we're going to use n and p again here for the mean. It turns out that the mean can be found by simply taking the number of trials and multiplying it times the probability of success, and that is it. That is all there is to it for binomial distribution. Let's do an easy example. Let's say, in our example, let's say n equals 30. Say we're going to perform 30 trials of something, okay? And let's say the probability of success is, what should we say? What's the probability that we're successful in one trial? Let's say it's only 0.2, okay? Well, the average or mean number of successes out of 30 then is 30 times 0.2, which is 6. There it is. There's the mean. 6. What does that mean? That means that is the most likely thing to occur. If the probability is 0.2 and you've got 30 trials, you can expect to have success 6 times out of the 30. That's what that means. That would occur. That would be the highest probability of any of the numbers from 0 to 30. This would be the highest probability. Not very high, but it'd be the highest of all of them. Okay? Now, the standard deviation. The standard deviation formula is a little more complicated, but not that much. We can find the standard deviation. Basically, if you stop and think about what the formula was for just all probability distributions in general, it was pretty complex. Here, for binomial distribution, it is simply the square root. It always involves the square root. You take the number of trials. You multiply it times the probability of success. Look familiar so far? One more thing. We multiply it also times the probability of failure. And again, you should recognize that we represent the probability of failure with the letter Q. And recall that the probability of success and the probability of failure are complement numbers. So let's take this example here. If n equals 30 and p equals 0.2, then Q must equal the complement of 0.2 because there's only 2 outcomes. So, if Q is 0.8, then my formula for the standard deviation, sigma, lowercase sigma, becomes n 30 times 0.2 times 0.8. And this is all inside the square root sign. Let's do that. Let's take the calculator. Get your own calculator. I'll get mine right here, and we'll see what we get. Turn it on, and we're going to do the square root, that second function of x squared. Now, enter 30 times 0.2 times 0.8. Probably can't read it, but that's okay because you're doing it yourself also. and that is equal to 2.1908, 2.1, just lost it, yeah, 2.19089 we'll say, and because my values for x are all whole numbers, namely the numbers from 0 to 30, they're whole numbers, I should be rounding my mean, actually my mean, if I want to be technically correct, this mean should be 6.0 to show that it's accurate to 1/10. I also want to round my standard deviation to 1 decimal place, so that would be 2 point, as 9 says to round the 1 up to a 2. There's my standard deviation. All right, now let's go one step further. Let's build the normal, usual range of values. Again, we know that it starts with my mean of 6. I know I'm going to go 2 standard deviations to the right, larger, 2 standard deviations to the left. 2 standard deviations would be 4.4. Add that on the 6, that will take me up to 10.4. Going 2 standard deviations to the left, that's 4.4 from 6.0. That should be about 1.6. So this comes down to be about 1.6. So we're saying if we have a binomial distribution with 30 trials, and the probability of success for any one of those trials is 1 out of 5 chances, or 1/5, 0.2, then what we can normally expect to get if we perform this, if we perform the action 30 times, we can expect to have success on a normal basis, anywhere from 1.6 times to 10.4. Well, remember x, they're all whole numbers. So really what that means is in terms of actual whole number values, they have to be a number bigger than 1.6. So the biggest whole number bigger than 1.6 is 2. And the biggest whole number can't be any bigger than 10.4, so that means 10. So in terms of actual successes, which are whole numbers, which are discrete values, not continuous, a probability distribution for binomial is always dealing with discrete values, whole numbers, is anywhere from 2 to 10. We would normally expect to get some number from 2 to 10. 1 would be unusual. 0 would be unusual. Anything from 11 up to 30 would be very unusual. It would be a rare event to have that many successes out of 30 with this low of probability of success. Okay, so there's an example of finding the mean, the standard deviation, and then using that to calculate our range of normal usual values for this distribution.